very happy to welcome Błażej. Okay, so so we are very happy to welcome Błażej Wróbel from IMPAN, Wrocław branch, and the title is Dimension-Free Estimate for Discrete Maximal Function.
Thank you very much. So first, thank you very much for the organizing of the seminar, to invite me here, to be here in Warsaw at your seminar. So I'm going to speak about the subject which is really in harmonic analysis, but there will be some small connections with ergodic theory at some point. I will try to make my talk accessible to people interested in analysis. So let me start with this. So the title is about discrete maximal operators, but I will need to start about stating similar setting and problem for continuous averaging operators. So the first part of the continuous Hardy whenever I will write HL, I will mean Hardy-Littlewood from now on. So the setting is the following. We take G at symmetric, and by symmetric, first of all, it's a subset of R3. So a symmetric subset of R3, by which I mean that X is in G even only if minus X is in G. Compact, convex set with non-empty integer. Okay. And then for we will write EG to the dilation of T. Okay, and easy examples of such sets are the BQ balls, which will appear later in the talk, so bear in mind what those are. So, for example, BQ balls. Okay, use one. Okay, and we define for initially for f infinity of Rd intersected with one of Rd. From now on, whenever we write capital L with some exponent, we mean Lp of Rd, and then later we'll have little l, and it will mean small Lp of Zd. That will come in a moment. So for those functions, we define the averages. MTG f of x equal the average over the dilation Tg of the shifted function. And this is a Hardy-Littlewood average. Okay. T is a parameter which is larger than 0. X is in R. So this is an average of the function. G is a symmetric convex set. Symmetric convex set with non-empty. By the way, this will be called the symmetric convex form throughout the talk. This is the terminology. Okay, and then this is a Hardy-Littlewood average, and we'll consider a Hardy-Littlewood maximal operator, which is just the supremum over those averages. So for those who have encountered these operators in harmonic analysis, this is the center Hardy-Littlewood average, and then will be the center Hardy-Littlewood maximal operator. So all of those will be the center operators that I consider here. So then we consider M star. Whenever I write the star, it just means that we take the supremum over T. M star G of f of x equals the supremum of T greater than 0 and Tg f of x. This is a pointwise supremum maximal operator. Okay, and now on RD come from this functional. So essentially one can rephrase this into saying that we are taking averages over any norms, any dimensions of any norm on RD with respect to this generating set of the norm. Okay, and then why are these operators important, say in harmonic analysis to begin with? So why are these operators useful or say important? So one point is that this is a say harmonic analysis point of view for the time being. So they dominate many other maximal operators. And now if we write explicitly an example where such a domination holds, so for any, say, for example, for any phi which is radial, has integral 1. We have the following inequality. If you take the subprimum, which is greater than 0 with minus t. And this is pointwise controlled by one particular family of operators, which is the Hardy-Littlewood operators over the balls. So you see I took any kernel, and as soon as it's radial, which has integral 1, and we have pointwise inequality here in this form. M star, not NEG but P2, which is the Euclidean ball, of X. So those kinds of operators appear quite often in harmonic analysis, not only for radial functions but also for another. But for radial, we have a pointwise inequality with constant 1. This is a known fact from harmonic analysis. So it controls a number of other operators, larger sum of all of them. Later we will see this also in the discrete setting where it's somewhat related to some ergodic theoretic operators.
Excuse me, because I haven't seen such things for like 20 years or something. So is there some natural behavior with respect to t? So is this supremum, does this happen at t equal to 0, at t equal to infinity, or it happens wherever it wants to?
I don't know if this has been investigated where it really happens, because it heavily depends on the function, on the input.
Okay.
Because it's MTF, so where the supremum happens depends what the function was.
Okay.
So I think it's hard to tell where, but that's the point of this is to sort of, I think one work on the kernel level and on the function level, and then you'll see in the proofs how it goes. That you split the operators in some part, and you don't really wonder where the supremum happens. That's an interesting question, because the approach is not that you want to really see where the supremum happens, take this t and estimate, but you rather want to estimate it with some other operators for which you know that you have a control.
Okay.
So you don't want to compute the supremum, essentially.
Okay.
On the other hand, this is actually related with what I will say in a moment, because I'll be interested in the size of the constants, which maybe for this it would be good to compute the supremum, but because you have a huge availability of a function f, I don't think you can naturally conceive that you can compute the supremum for any f, arbitrary f, because the input function is arbitrary. So I think you can compute it when, for example, when the kernel was Gaussian and the function was Gaussian, it could be computed, but otherwise, I don't know if there are many instances like this. Yes?
I cannot read the first line.
For any phi which is from R to C,
Yeah.
and it's radial. And has integral 1.
Radial.
Radial means that phi.
Okay.
Yes. So it only depends on the length of x. So this is what it means. So but apart from that, it's arbitrary. Sorry, not completely arbitrary. Radially decreasing. Sorry, forgot. So phi 0 decreasing. At least in the classical proof, I think we can make it for any functions. But the point was that it dominates a number of other but I'm really interested about some inequalities for norms of the operators. So let me first say what do we know about the norms of these operators. So what do we know? So first, one has a trivial bound on L infinity, because this is an average, so the L infinitum of an average is less than the L infinitum of the function. So trivially. So this holds with constant 1 without any effort. But then one of the first things one learns when I read the book from harmonic analysis is that this can be extended to LP spaces. So the way to do it, usually you start with not with a generic set but with a ball. But then if we are not interested into the size of the constants, then any such a set contains a ball and is contained in a ball. Because I said that it's compact and this has no empty integer. So it can compare it can be compared with the operator for the ball. The problem is that the constants, we have no idea what the constants are there because of this comparison. So if it contains a ball, say, of radius r, then the constant will be raised to the power d. So not interesting in regards to what I'm saying later, but anyway, one can also show, let's say, classical result from harmonic analysis. Is that there are bounded on everything. So M star G F LP is less than C depending on P, depending on G, and depending on the dimension. And the LP norm of F. And this holds only for P between 1 and infinity. So by the way, there are also some questions about the weak type for these operators, but I'm not going to mention them on the talk. So we always stick with P greater than 1. Okay, so this, when we are in dimension 1, then essentially there is only one such a symmetric complex set, which is the interval. And then this is basically due to Hardy-Littlewood. This is what they studied. Actually, they studied a discrete version of it, which implies the continuous version. But then for more general, so let me write. B equals 1 is basically Hardy-Littlewood. I don't know the exact dates, but it's 20s or earlier. Okay, and then B greater than 1, I think it was first proved by Calderón and Zygmunt in the 50s. And as I mentioned, this constant in the classical proofs, it depends on everything, on P, G, D, and G. Okay, so one line of the investigation in the maybe okay, let me mention again how it depends. So in this case, we use the Calderón-Zygmunt proof, and P is fixed, and say G is the ball. For example, the constant is like 2 to the D. And the reason is that in those proofs you use a doubling property of the Lebesgue measure, which means that at some point you will use that the measure of twice dilated sets is proportional to the set itself, but the proportionality factor is 2 to the D. So maybe let's rewrite this comment. So what about the size of C E in terms of so I will speak about the size in terms of D. So P is fixed, we'll only worry about the size in terms of D. Okay, so as I mentioned, the original proof. Calderón-Zygmunt. Even for the balls. show that C of P B B2 is controlled by a constant which depends only on P, independently of dimension. And this, as I said before, I always consider only those P's.
But the first result said something that it does not depend on P, because it's like when you wrote the first line, the Calderón Zygmunt.
No, so okay, so I did not say it's an optimal constant. It's so their proof gives a constant of this order.
But independent of P.
Okay, it should be depending on P as well.
Okay.
So let's think that P is fixed, and then we can forget about the dependence. We are not worried about dependence on P, but it depends on P. So this one gives something like this, to be explicit. This one gives something C of P which is worse than that, but does not depend on P. But let's view all of what I'm talking in this way, that P is always fixed, and we want it to be independent of P. So when I write inequalities like this, without even the P, it implicitly means that P was here. So P is always fixed. I don't want to move P. I want to prove something that does not depend on D for fixed P. But you're right, it would be contradictory if it was the other way around. Okay, so this was like 182, but then 4 years later, Bourgain proved something even more surprising, at least to me. Even more surprisingly. In 8, I think 6, Bourgain proved that this, at least when P is equal to 2, this holds for all symmetric convex sets. So what do I mean? Maybe I write it in the norm inequality now, not about the constant. So he proved exactly this, that n star G L2 to L2 is bounded by a constant. And not to worry about what the constant is, I think 1000 is enough. Okay. So he proved that for any set G in any dimension, the full maximal function has an L2 bound which is bounded by 1000. For any symmetric convex sets. Okay. So Stein's proof relied very much on the fact that you had a ball here, because the ball has a nice property that essentially it has two good properties. First of all, that a maximal function from the ball is controlled by a maximal function for the sphere. And spheres have some property that if you average over a sphere of high dimension, it can be seen as an average of lower dimensional spheres. So there's some relation between balls and spheres and monotonicity that allows Stein to prove this. This is a very point of, like over the top point of view of this estimate. I don't want to go into the details. Bourgain's approach was more related to something called asymptotic convex geometry, because he was coming from Banach spaces and he knew about convex sets and this kind of stuff. So this is related to, proof of Bourgain is related to asymptotic convex geometry. And maybe you have heard the term isotropic constant. So this is where it's one of the places where this constant appears. Isotropic constant for a symmetric convex set is needed here in the proof of Bourgain. Okay, so I also wanted to mention that this inequality of Bourgain was also one of the reasons that were mentioned in his fields medal citation. This inequality on the for general symmetric convex sets. Okay, now let me, once we reach this point, I can state one of what I believe is one of the most important open questions in our harmonic analysis that are not solved. but now let me call it the continuous maximal function conjecture. And as the name says, it's a conjecture. So essentially it asks if this what happens for p equals to 2 happens for all p's. For each between 1 and infinity, there is C of p, and by writing it this way I mean that it depends really only on p. C of p is such that m star g equal to is bounded by C of p. And as before, I don't care what is the dependence on p. I mean, it can be quantified in many instances also in Stein's paper it can be quantified, in the Calderón theory it can, but from this point of view I don't care what p is. Sometimes it is that p equals 2 is the most important thing, and then it's just p equals 2. But not for this conjecture. So it asks that this holds for all p's between 1 and infinity. Okay, so let me say what is known. So this is like from slightly, I mean, in 82, 86 Bourgain proved this, and then my impression was that people were trying to really prove this for several years, but then it sort of got stuck. So it's like for 40 years, more or less it's open. So let me make some marks. And partial progress was made slightly after by Bourgain and Calderón. Almost this, I think it was essentially the same year. So Bourgain proved this, and then after having dared to estimate, both he and Calderón could push the range of p's, but not to 1. So partial progress, this is like 86 or 87, Bourgain and independently Calderón proved that this holds for p greater than 3 over 2. So, maybe it's a good point to mention why we care about the size of the constant and just we don't want to compute the norm of the operator. Maybe it's achievable, but apparently not, because even in dimension 1 I think the norm of the Hardy-Littlewood no, sorry. Okay, I'm not 100% sure it is not known when d equals 1 what is the norm of the Hardy-Littlewood operator, the one corresponding to intervals, but in any other dimension it is not known. So nobody knows how to compute it, and perhaps people were thinking maybe we at least can try to estimate it. And even if we don't know how to compute it for the balls, it's pretty unimaginable that we will be able to compute it for general symmetric convex sets. So this is why this line of research came from. Okay, so this is like from 86, 87, Bourgain and Calderón, and then several years later, for BQ balls, we have a result of Miller from 1919, and then complemented by Bourgain in 2014. That this holds within the regime of BQ balls. So if we take a fixed Q and we consider a family of BQ balls, growing depending on the dimension as well, then Miller proved that this is true if Q is between 1 and infinity excluding infinity, and then Bourgain 14 days later proved that this is true also for Q equal to infinity.
Wait, for all p's then?
All p's, exactly. So this is the point. It holds for all p's, but depends on Q. So maybe let me write the explicitly. Miller is that M star BQ. I write BQ of D here because the family depends on D as well. Is less than C of PQ, not depending on D, but P is anything from 1 to infinity. But Q is restricted from 1 not including infinity. And then Bourgain in a way that this does not explode when Q goes to infinity, it would cover the other case, but it is not working in this way. So this is the point. So actually what is already not known is if the constant does not grow when Q approaches infinity, because we have two sort of separate proofs. One says that this is bounded by C of PQ for Q up to infinity, whenever we fix a Q which is smaller than infinity, and the other proof says that at the end point, it does not depend on the again. But it's not that they together say that this does not explode when Q approaches infinity. So this is sort of a maybe first instance that something is not known and can be maybe investigated. Okay, so this is about, I needed to make this long introduction to motivate what I'm going to write now. So let me now move to the discrete Hardy-Littlewood averaging operators. This is, I think, especially useful because in the discrete setting, some of these conjectures are impossible. So you need to make some other and try to put them this way here.
Known for some other natural families of sets?
No. So this is the only case
like squares or something.
Okay, so for that it's known because essentially this constant is independent. So G was a generally symmetric convex set, and when you apply an invertible linear transformation to it, it's still a symmetric convex set. So it is up to those kinds of transformations. It is the norms are preserved. So you cannot, like for example, it's known for the ellipsoid because the ellipsoid is just a shrinkage of a hole. So you cannot make other convex sets which will violate it out of those that you know. But it is, for example, not known if you take, let's say, I don't know, I take the cube in 2 dimension and tensor product with a ball in 2 dimension and do it a lot of times, and then it's not known for those kinds of sets. So you can imagine some sets for which is not known, but but they are more complicated than that, and they cannot be just linear transformations applied to those that it is known. So let me now move to the discrete setting. So G is again the same, it's a symmetric convex set. Symmetric convex body. So again, it was a symmetric convex set with non-empty integer which is compact. So a ball for some norm on the Hardy space. Now whenever I write LP, I will mean LP of the integer lattice. So capital LP was the LP depend on RD, and now this is the LP of the Z space. Okay, and we define for any f from Z to C. Now I write it like it was a function, but I mean it is a function, but it's a sequence, double-sided sequence. So we take Hardy-Littlewood averages, discrete. So this is a script n. So in the continuous case, I was writing the, say, Roman style n, and now it's a script n. So this is n t g f. Now I want it to be defined on functions which are from ZB. So instead of the integral, I write a sum. And I want to compute the sum on the integer lattice, so I'm intersecting with ZB. I want to have the same as it was before, so f of x minus y, but now I want to be an average, so I divide by the number of elements here. It's divided by 1 over the number of elements in EG intersected in Z. So this is the averaging operators in the discrete Hardy-Littlewood like it was in the continuous operator. It will be very similar, because if T is very large, then the number of lattice points resembles very closely the Lebesgue measure of the set. So you can expect that they are very close when T goes to infinity. But when T is small, they are not very close.
But G is unbounded.
No, G is bounded, it's compact.
So you obtain just one.
Sometimes, but sometimes you obtain, like for example, for the, depending on T. So if T is very, very small, like
Yeah.
it's, I don't know, goes to 0, then you obtain just 1 point.
Yeah.
But in some regimes, you obtain a number of points which does not correspond to Lebesgue measure, but it's not 1, it's like 2 to the T or something. So it's easily seen, let me write it, since you made this comment and you make a passage to that. So you say T is the Euclidean wall, then if I want to compare this with the Lebesgue measure, then the Lebesgue measure is this, T to the T, and then I don't remember exactly, but the Lebesgue measure of the ball is very small, it's like factorial. The Lebesgue measure of the d-dimensional ball is something like 1 over d factorial.
Yeah.
I'm not exact, but of this sort. So even when T is like a constant times d, this is already very small. So this is going to be a lie because I didn't remember the formula exactly, but it's something like 1 over d factorial, say, not exact. So this is like T to the d, and d factorial is like d over e to d.
You intersect with Z power D.
You see d, yes.
So this is discrete set.
This is a discrete set, yes, but I'm saying that for some points, this is already very, very small, but the factor that is here is not so small. So there is some regime when it's trivial when T is very close to 0. Then it's trivial because there is just 1 point.
Yeah.
Yes, and when T is very, very large, it's like in the continuous set.
Yeah.
But in between, who knows? So this is the problem. So that in between the problem. The problem lies in between. Yes, exactly. And in a moment that this will be quantified more, but exactly, this is the good the observation is good in a way that the problem is really in between what happens. Because when T is 0, there is no problem. When T is very large, it's like continuous, but in between, it's neither. So we will have to work. And the problem, this field is always hard, and we'll see in a moment what I mean by that, because you don't have dilations. So it's not that if you dilate the set, it's not that if the TG intersected with GT, if I know the measure of this, I don't know the measure, the number of lattice points here, I don't know the number of lattice points in any dilation. At least not direct. So you don't have dilations about it. And this is what makes problems more difficult.
Wait, so and you will you be trying to get something similar to that? So will you be trying to drop the dependence of D at some point?
Exactly, and this sometimes it can be done. In general, it cannot be done.
Okay.
And I will say an explicit result which says that this conjecture fails, the one that was there for all discrete. But in some of them, it can be true, and I will also mention some results where it can be proved.
Okay, because I was going to ask I was going to say that, for example, for D equal to 2, then you can get I think you can get an easy formula depending how this depends.
Sure. In any fixed dimension, you can get a formula how this depends, because
depending on, I assume, the measure of the boundary and the measure of the
exactly.
set.
So the main term will be always the Lebesgue measure of the set, and then there will be some error terms, and you can work it in fixed dimension. But the point is that I would like to make D go to
Drop
infinity.
this dependence.
Yes. And then it's hard to even if so G is anything. So for example, if G was, let's say, the cross polytope, the thing corresponding to the L1 norm. Sometimes people in combinatorics sometimes call it this way. So L1 norm, sometimes it's called cross polytope. I don't know why. Yeah, because sort of when the number of dimension grows, it's most of this massing is on the axis. So this is the justification for it. Okay, anyway. But even for this, there is a direct formula which says how the number of lattice points behaves, but it's hard to control it when the dimension grows. So this is the point. You have to devise the tools which will allow you to be able to not to include the dimension in your computations or in your estimates.
If you replace ZT to some discrete group and discrete, then maybe
that's possible, but because we don't really know a lot in this case, then we didn't move to the other. So I will say in a moment that we like know something, but not a lot. So, but that's a good yes direction of other research. Okay, so I defined those averages here, and then maybe let me erase this.
Just to comment, so in the case of amenable groups or groups in general, this is related to Keston's theorem stating about the norm of averaging operator, basically that amenable group is less or equal to 1, something like that.
What
finely generated group, and then this kind of average indicator is norm less or equal to 1 if and only if norm 1 if and only if the group is eliminable.
But you're speaking just about the average, not the maximal function, yes?
Yes.
Okay. I see. Didn't know about this. Okay, so I introduced the Hardy-Littlewood average, and now the maximal function will be like before. So m star gf(x) equals sub over t greater than 0 m t g(f)(x). So this is the Hardy-Littlewood discrete maximal function. Okay. Oh, and by the way, one remark I wanted to make is that because we are making, because in the summation here and here we have just a number of lattice points, and here we are intersecting with the ZD lattice. This function has actually jumps. So it is constant up to some threshold, then it is constant again and then again. So for example, for the cube, one can easily see that it has jumps on the natural numbers. For the ball, you will have jumps on the numbers of the form square root of m when n is a natural number. So it's not really a full subprimum over full t greater than 0. It's never like that. It's a subprimum over some discrete set always. Like this. Okay. So yeah, why is it interesting to consider those operators? Consider discrete settings. So one of the points is that part of a branch of harmonic analysis called discrete analysis and harmonic analysis. It's more like motivation for harmonic analysis people. So a branch of analysis. So this was initiated by Stein like maybe 30 years ago. This. So basically one takes objects of harmonic analysis, tries to make the discrete versions and see what can be pushed. But then another perspective to say that it is interesting, this is easier seen for those discrete operators with some connections to some other fields that forgot to continue with one, is that if I just look at the thing that is in the denominator here, we need to count the number of lattice points in something. And this is either related to combinatorics, and the radius will be very small, or to number theory, when depending on the type of the sets of G. So it has been clearly because we have this in the denominator, it has some relations with combinatorics and number theory. So relations with combinatorics and then okay. And the next point I wanted to make is that these operators are harder than the continuous ones. And this can be quantified in a very strong way, where you write a result which says exactly that. So estimate for m star G is always harder, harder than for n star G. So this is the discrete, this is the continuous. And by this I mean this inequality. M star G, this norm from LP to LP is bounded with constant 1 times the discrete norm. So this is a result from 2023 of my collaboration with Kosh, Mirek and Calderón. So it says that if you know how to control the discrete constant, you always know how to control the continuous constant, but well, not exactly vice versa, as we'll see in a moment. And so this means that trying to obtain an estimate for this, it's harder than trying to obtain an estimate for this. And then there may be instances when this is say it does not depend on it, and the other does, and indeed there are instances like this.
But functions are defined from different.
No, so this is just a norm of the operator. So I wrote it explicitly in this way to forget about writing the function. So if you want, I could write it like this. So this is just the sum.
Norm.
You see, it's the norm of the operator from LP to LP. It says sublinear operator, but you can agree that the norm is like the usual norm. So yeah, right, sorry. So maybe I was a bit confused. There are no functions here, just norms of operators. Okay, so yeah. So another point is that dimension free inequalities like this. Are impossible in full generality. And by full generality, I mean arbitrarily. And so this means that this conjecture, the continuous, is there is already not. So this is the continuous conjecture, but it's not true in the discrete circle. So I can quantify it in this way. For each dimension, there is a specific symmetric convex set and an ellipsoid actually. There is a very easy ellipsoid. An ellipsoid E of P such that n script star E of D this LP1 grows in P. But it cannot grow for an infinity because at an infinity is 1. But apart from that it grows. So it says that there is no chance to have a conjecture like that on any P. So yeah, and this is a result of me with Bourgain, Mirek and Stein from some 2018. Okay, so this means that there is no chance for a conjecture like that, and it means we need to focus on specific kinds of symmetric convex sets to achieve anything. Because, I mean, it destroys the hope to prove it in generality, but maybe it holds safe for the balls or for the cubes or who knows for what. Okay, so yeah, so as I mentioned, this ellipsoid is very explicit, and the failure of this cannot really happen on for large T, because as I mentioned, for large T it should be like a continuous set. So indeed it happens for very small T's in failure. And another point to observe is that this sort of tells what did I mean that there is no dilation invariance.
But not too small. Very small, but
Not zero, but greater than 1 is already
I assume it has to be big enough for the boundary to be very bad for the like the relation between the boundary and the lattice. So it has to be big enough for this to be nasty, but obviously small enough for the measure of the set not to play the greater role.
Yeah, yes. So actually, in this case, it is that this ellipsoid is made in a way that when you increase the T's, other parts of the versors are added to the set. So there is a range of T when you really consider this, and when T is 0, there is just the 0 vector in the set. When you take T, the second index which we are interested in, you add 2 versors, E1 and plus minus E1. When you move it slightly afterwards, you add 2 another versors, plus minus E1 and plus minus E2, etc. And there is some interplay. So like you don't really go very far for this to be broken, but you cannot stay at 0. And another point is that this also says that any dilation invariance does not make any sense here, because if you are happy with sets which are isomorphic with respect to linear transformations, then the ellipsoid is a ball. But now I will say in a moment that for the balls you have some results. So okay. So and there is another point that is interesting. There is a conjecture here which might be true, and it is 10 years younger than this one. So let me write it a bit here. conjecture was made about the balls, but the ball actually, in regards to this kind of estimates, is more difficult than the cube in some instance. So now I will try to. Before that, I would like to make a connection to ergodic theory, and I will try to tell you what kind of results are valuable. I have time until quarter before 1. Yes?
Correct.
Okay, so another point that is interesting, and this is the point of connection with ergodic theory, albeit quite not a very strong one, is that it has relation with some kind of ergodic averages. Maximal function estimates for commuting and invertible, for ergodic averages of commuting and invertible linear transformations. So I take now that T1 be a system commuting measure preserving, not linear, sorry, commuting measure preserving transformations. Ergodic averages similar to those averages on Z. So we consider this. Consider A and G, f of x. Count the number of lattice points in ZD. So this is the same, the factor in front. And this is also the same. But now instead of just taking the lattice ZD, we take f composed with those transformations. So T1 composed with 1, Y1, T2 composed with Y2, TD composed with YD, applied to x. So this is an average over a function with respect to those ergodic transformations. When the previous setting is also like this, but the ergodic transformation is just the shift by one coordinate. And it turns out, by some principle called Calderón transference, that these kind of operators are dominated pointwise by the ones that I wrote before, in terms of norms, and in terms of variational norms as well. So let me write it maybe. So in a way, this is the ergodic setting which dominates all the other ergodic settings, in this regard at least. And similar thing can be proved for the variational semi-norm, which is sometimes for people in ergodic theory is more important because I don't know to write what that is, but it gives immediately pointwise convergence, the other objects. So this one not you need to look for a dense case, and sometimes it's problematic, but there is an object called the variational semi-norm which also has this property. You replace maximal function with variational semi-norm here, and here it also holds, but the other is more suited to pointwise convergence problems. So this means that it's sort of the, if you are interested in the size of those constants for ergodic, for those kinds of ergodic averages, they are always smaller than those. another thing that it means is that if you are able to prove this for a certain class of sets, and let's say for the Euclidean balls when t goes to infinity, it immediately means that this does not depend as well on the number of the coordinates here. So yeah, so this is one other point. And now I would like to overview some existing results of this kind and finish by showing you what is really the core of the proof. So I will write you some estimates for Fourier transforms, which if you know, you will be able to prove these results. And some of them are known to us and some not. Okay, so yeah, maybe let me know.
Let me, because I must admit it's a little bit strange to me from an ergodic point of view, but maybe I don't get it, because we will have a sequence of Fellner sets. So so this would, I guess, corresponds to taking bigger and bigger t here.
I'm not 100% sure. I mean, it's a, so you see, it's a way to generalize it to ergodic theory, but I'm not sure if it really corresponds to what you usually consider. So
I see. Okay.
So it's not that I'm saying that it's like maybe this is why I said that it's a sort of a maybe an artificial connection in a way, because you make those kinds of averages. So it's maybe a realization that it works not only for z shifts but all of kinds of transformations. But I'm not sure how it relates to what.
No, to consider a family of commuting transformation, that's very common. But then you think about the group that is acting is ZD, and now you will take Fellner sequence and try to understand how when these sets are bigger, you average with them, and you want to understand the limit.
Okay.
But here it's not limit, it's supremum, so t might be just some finite number.
Yeah, I know, but usually if you know this maximum function, you know everything, right? But but from the, why would you like to study this TG? This is my question.
So for example, one point that your question reminded me, so you can think, for example, if you, let's say that you are able to prove something for the variation seminar, because it implies almost everywhere convergence. So if you know that this is finite, you for example know that the limit when t goes to infinity exists, which is not maybe immediately available. It is if the function is bounded, it is zero, but so no, it's not obvious if the limit exists, for example, when t goes to infinity, because any other point when you want to consider the limit here does not make sense, because this is a discrete set. And also,
when you say limit, you mean pointwise?
Pointwise.
Yeah.
I mean pointwise. For example, you can from this you can get pointwise convergence when t goes to infinity. So this is the interesting.
Yeah, that's very interesting.
Yes,
I agree with you, but
on any other points do not make sense, because you cannot consider t go to t0, because if it's a stepwise constant function. So the only interesting limit you can get out of it is when t goes to infinity. Yeah, and this gives something, but maybe we can talk later, because yeah, it would be nice. Okay, so yeah, so this holds, as I mentioned. Now I would like to sort of overview what is known, and then to give you some insight of what estimates we really use to prove the results. So this is the point screen. Functions. Now existing results. So first result I would like to write is this thing that I mentioned, that if t is very large, then you can compare discrete to the continuous. It's always, from this board, it follows that discrete is always larger, but when you take the subunits for t which are large enough, it's the other way around as well. So let me write the proposition. But before that, I need to introduce some quantity. So I find some constant c of g to be the smallest t such that smallest t greater than 0, such that the unit group is contained in T. So this was a open set with non-empty integer, so it always contains a cube of some size, and if you dilate it small enough, it will contain large enough, it will contain a cube of this size. So I introduce this constant, and then by the way, this can be also written in several ways. So like one is that it's a supremum over S in the unit cube. And now I write the G norm of the Minkowski norm corresponding to the set G here. And then another way to write it is that it's 1/2 of the norm of the identity operator acting between two RD spaces. So just several equivalents here to express this. Okay, and in terms of this quantity C of G, you can write the threshold where continuous dominates the discrete. Now I'm just mentioning theorems which are kind of transference theorems that will allow you to transfer something from continuous to discrete, but the most difficult part will be when you cannot do it, and then you will need to have some Fourier transform estimates. So this is again Mirek, Stein, and myself. So it says that there is a comparison for large enough. So supremum over T greater than C of G and D and T G F LP smaller than e to the 6 times the norm M star G capital LP to LP times the LP norm of F. So what does it mean? If you restrict the supremum to large enough indices, there is a control. I mean, e to the 6 is okay because we just want to, we don't want to compute the norm, we just want not to depend on G or whatever. Okay, so, but the problem is that what is this C of G for various sets? So, it will hold for T greater than C of G, but we need to see what this is. For example, okay, so as I mentioned, this reduces controllability of the maximal function to reduces the problem to controlling supremum or T smaller than C of D. At least it does so when we know about this operator, but in many instances we do. For example, when P is equal to 2, this is always a finite constant by the result of Bourgain. So when we just think about P equal to 2, you can always say that we are reduced to this kind of suprema for small t. Okay, but for example, for the BQ walls, have this. And this constant is equal, copies the way down by 2, and D to the 1 over Q over 2. So already you see that there is a number of points. Here in this set, there will be a number of points. It's not just one point will be here. C of G is large, multiplied by D is even larger. So it's not trivial. If you want to compute, if you want to control the norm in terms of a dimension 3 constant, it's not trivial to do. If you just want to say that this is bounded, this is trivial because the number of points T in this set is finite, and you can just estimate it by sum of the supremum can be estimated by the L1 norm, and then you use triangle inequality and you get what you want. But you just want to make it independent of it, so then it's not trivial. So for example here, for the BQ walls you have this, and then this means that T, D times C of G, is of the level D1 plus 1 over Q. So you need to think about smaller intervals here. Okay. Okay, so, but for some ranges of for some ranges of Q's you can push this to a lower level, and I will state the result which combines this observation. Q is into infinity. q equal 2, and then for q between 2 and q equal to, sorry, and infinity, and for q between 2 and infinity it's due to and then, so this is like from 23, and this is from 19. Okay, and then we also have some partial result for q equal 1, because observe what happens for q equal 1. This is true for all q's. So when q is equal to 1, this is d, which means that this general transference gives the range of d squared here. But it can be pushed to d over 2. So, over q equal 1, we have but as I mentioned, these kinds of results are kind of a transference estimate. So you need to realize how far you can go to compare the discrete to the continuous. But the really maybe more difficult part of the matter is when the radius is small, what to do then. And then in some cases you can do something, and I will now write what you can do in each cases. And at the end I would like to showcase the Fourier transform estimates that are there. So now we try to go beyond these kinds of comparison principles. So what remains is small scales. And now I'm just speaking about the q equal 2 and q equal infinity, because these are sort of the simplest symmetric complexes that you can imagine. You give them more and so in this case, if we are interested in t smaller than d, more or less, because as I mentioned here, this holds for t greater than d, we are okay, or for 2 and only t smaller than d interests us. And then what really is the key, really R estimates for Fourier transforms. Fourier transforms / Fourier multipliers actually. Multiplier symbols. So we consider those kinds of functions and the q of psi. This will be the Fourier symbol or Fourier multiplier corresponding to the averaging operator. So the definition is this. You take what was there with respect to the q ball, and as I mentioned, we are really interested in q equal to 1 infinity. Then you make the sum, as it was there, and then you take the exponentials here. Right. This is the inner product with psi. And now psi is taken from the torus, the d-dimensional torus, which is just essentially the set minus 1/2 the p device. So if we work on RD, I will just take the Fourier transform of the set here, but now I'm not taking the Fourier transform of the other Fourier series. So ZD corresponds, if the function is from ZD, its Fourier transform will live on the torus, and vice versa, if the function is on the torus, its Fourier transform will live on ZD. And now I will write three estimates that if one is able to prove, one by some other machinery that we know works, can give you some conditional results. So I write three Fourier transform estimates, and then I will say that if we have those, we have some some result for the maximal function. Only that you should keep in mind that there is some machinery in beneath. So it's not that if you see it for the first time, I don't think it's easy to reach to the conditional statement, but there is a machinery that you can avoid. Okay, so those kinds of estimates, which Fourier transform estimates are useful. So one is for the difference. It goes like this: m p1q minus m of psi minus m p2q psi, and this has to be controlled by. I will write this with the meaning that there is a constant about which I don't care. It does not depend on t for sure. So and then I will keep writing c all time. So this is t1 minus t2 max t1 inverse inverse. And this I will call d, the difference estimate. And then another estimate is at the origin. And it goes like this: m t q of psi minus 1. This has to be controlled by t psi over d to the 1 over q. And this is an estimate at the origin. By origin I mean that it's really useful only when psi is small, because these are Fourier multipliers. The exponentials have modulus 1, so this is always smaller than 1. So this is only interesting when the length of psi is small. The length of psi is the sum over psi j squares. But note that because psi is from the torus, this is really always smaller than the square root of b. Okay, and the last estimate that will be useful is an estimate at infinity, and it goes like this: mq of psi smaller than the same but in the denominator. Now I will state a conditional result which relies on these three estimates. So the conditional result is that if we assume you give those three estimates, use some little theory, some theory of Markov semigroups and some other stuff, then this result can be proved that I mentioned now. If we know that those three estimates hold. So result is the following: if first let me give a dyadic version, which means that the subunum is restricted to a dyadic set. Conditional or maybe okay, sorry, I will write it all together. Conditional assume that d or y hold, then we have m star bq lp of zb lp of zb is controlled by a constant which does not depend on d, depends on p and depends on q. That's it. Or c of p in the range p greater than 3 over 2. So as soon as for some q we have those estimates, we can prove this. Okay, and another conditional result is conditionally if only O and I hold without the D. D is the most difficult, and here I will mention in a moment why. So if only O and I hold, O and I hold, then we don't have this, but we have a dyadic variant, which means that the subunum will be not over all t greater than 0, but over powers of 2. Then m star dyadic supremum is very much restricted. So this means that the supremum is over powers of 2 volume. Okay, so you see that this is, I mean, if one can put those kinds of estimates, you can get this result. And I did not do it just to showcase that there is some estimate you don't know how to prove and you get this, but in some cases you can prove them. And the easiest case, as I mentioned some time ago, is the cube. In this case, in the discrete setting. So, theorem idea, when we say theorem, answers the question that when can we verify those estimates? We can verify them for the cube at least.
So that's mean for the cube when bq
When q is equal to infinity, it's just minus 1 to the power t.
Mhm.
So this is what I mean.
And then the case q equals 2.
We have some partial results, which I will mention.
So it's a conjecture.
Yeah, for q equals 2, even on because this I write that you can, using those, you can get those estimates for p greater than p over 2. But even p equal 2, the case of the p equal 2 and q equal 2, this is not known. The diatic version is known, this is what we proved, but not the full one. And I will mention that there are some partial results towards that. Okay, so let me first say that we can verify all of those three, p o 1 for q equals infinity. So this is the result from 2018, I think. Again, the same set of authors. Okay, so DOI all for the cube. And because they hold for the cube and this conditional result holds, we have an estimate for the maximal function. But why are they easier for the cube than for the other sets? Because that's because the formula for the multiplier is much easier for the cube than for the other sets. In theory, you need to count lattice points there, but if those lattice points are inside the cube, there is a very easy formula to write what is. There is an easy formula to write what is this for the cube, and even what is this exponential sum. So I write it down now and compare it to the continuous formula to make you see that there is a it's quite close to the continuous set. So this is possible because m t infinity of psi. The interesting t's are now natural numbers because the jumps we needed to count lattice points in the cubes, but the jumps happen there where you move where you are at the natural numbers. So those are the only interesting things. And the formula is this product. I mean, it has to be product because the set is product. Sine of 2t plus 1 phi sine k divided by 2t plus 1 sine phi sine k. So it's not that one gets it immediately, but after a little bit of work, one gets this. But I wanted to write it up to see that it's very explicit because you don't see any lattice points to be counted now on this set. Okay. And another reason I wanted to write it, I wanted to write the continuous counterpart of it to make you see that it's very, very similar. So if we were taking averages over continuous cubes, then the formula here won't be this one, but a very close one. Comparing with the continuous case, continuous cube. So let's say m infinity continuous t would be this. Product sine of 2t plus 1 phi psi k divided by, and now I will divide by something larger. So you need to divide here by this. Sorry. So the only difference between those formulas is that here you have pi psi k in the denominator, and here you have sine pi psi k in the denominator. So for example, it's not that if you know some estimate from this pointwise, you don't immediately know some estimate from, I mean, you do know some estimate, but you want the constant not to depend on D. So you don't know a useful estimate immediately from that. But they are very, very close. So this is what, this what I wrote here would be the Fourier transform of the T plus of the characteristic function of this group. This is the Fourier transform. So if you compute this, exactly this Fourier transform, you'll get this formula. So they are very close, and for this reason, you can try to, well, it's one point that makes you think that maybe you can prove some estimates, because estimates for this expression, when one of the main parts of the Bourgain's argument for general symmetric convex sets, only that he proved them for general symmetric convex sets, not for G parts. But they are true, this is what I mean. So for this, you know that those kinds of estimates that we are asking in D, O, and Y are true. So you can expect that they will be true here because the formula is close. And actually, I prepared some argument, but I think it's better to move to mention you what is known for the ball instead of writing details here. I wanted to convey the message that you have a very explicit formula and you can go with that. For the ball, there are two partial results that are known. But no explicit formula like this for the Fourier transform. Discrete Fourier transform. So not only for the ball, but for any other symmetric convex set, there is no such easy formula like that, no such explicit formula. So, what about no explicit but there are two partial results which I will state now. Okay, so essentially one is negative counterpart of what we would like to have there. So I said that the conditional result, which was fortunately erased, but it was here that we get three conditions: difference, origin, and infinity. And for the cube, you can verify all three of them and get the result. For the ball, we can verify origin easily, and infinity in some weaker way, which is still enough to get what I will write now. So there are some partial results. You can verify the condition of origin, and I will recall it now. For the ball, it will be this: MP2 of sine minus 1 smaller than a constant times t sine over the square root of t. Because here it was d to the 1 over q, for the ball is the square root. And then infinity normally would be the inverse of this. We cannot verify this, but for some ranges of t's, we can verify a similar condition which is enough. So you can, okay, the condition of the origin, you can verify the condition of the origin O, and weaker versions condition of infinity. I will write one weaker version which is not always what you have, but maybe it's insightful to see it. So let's say for t, the interesting range of t is now t smaller than d, and I will write a condition which you can prove for t smaller than the square root. It goes like this: mt2 of sine is smaller than 1 over t sine the square root of d. So this is, we would be happy if we had only this. But unfortunately you have some other term, plus 1 over t, and now I write sine plus 1/2 over the square root of d. So, okay, maybe I should write alternative So instead of, maybe I can represent it like this, that psi squared is the sum of, it can be written like this, orally. To make it periodic, because I wanted, this shift here means that you shift all of the coordinates by one half. So if this is the sum of sine squareds, then this will be the sine of cosine squares. Because of this gets multiplied by the square should be outside of it. So we don't really have this formula, but we have a similar formula like this, and this is still okay to work with because you can essentially split your frequency space when you work on these problems into the set where this is larger and this or the other is larger, and there are only two parts of the splitting. So then in the end you can combine. So because you have those two estimates, you can prove this result. One result from 5 years ago. So we were able to prove a dyadic version of it, but the full conjecture still remains. So it's not known if it holds, if it has a dimension-free constant in the full range. But this year with my student we were able to prove a little partial result towards that. So we justified that. A little bit because I will need to put minus epsilon cube, but that's better. It's not there, so we will restrict t even smaller to d to the power 3 over 4, you can get the full maximal function. So now what is, just to recapitulate what is known with this conjecture. The conjecture was that this is true for all these. So when t is greater than d, it's known it's by this comparison principle was there, but it's not there anymore. When t is smaller than d to the power 3 over 4, it is known, and then there is a range in between, and who knows what happens. So what we believe is that you can probably push this. Sorry, it should be 3 over 8. Sorry. So we believe that it can be pushed probably to one. If you work hard, this method maybe can be pushed to square root of d, but I don't know how large. And then the gap between the square root of d and d where some other methods need to be invented. Okay, I think my time is almost up, so yes, that was all I wanted to tell you. Thank you very much.
Are there any questions? Yes, please.
I have a question, but I think it might be well outside harmonic analysis, so feel free to ignore the question. So what happens if you change the setting slightly? So let's stay with the cubes or the balls or whatever you want, but instead of set ZD, take a maximal one separated set. By which I mean a set where every pair of points is of distance at least 1, and it's maximal in a way that you can't put any more points. Could any of this work in this setting?
I have no idea.
Okay, so it's well, because I assume the Fourier methods will not work properly then.
Probably. So you will need to have some Fourier analysis. For these methods to work, you will need to have some kind of Fourier analysis. So if they can be, maybe for some kinds of the sets you mentioned, there are some Fourier methods, there are some specific sets, but in general, if you don't have Fourier methods, then maybe for these comparison principles, there is a hope one can achieve something, but for when you really go to the heart of the matter for small scales, it's really the Fourier transform that works.
So you need the regular structure.
Yes. But on the other hand, I mean, we can't really prove the full conjecture even for ZD, so this is one of the reasons we did not go
Yeah, of
Sorry,
course.
but it makes sense probably, yes. As soon as you have the full lattice available.
No, it makes sense from the ergodic point of view, because this is a question actually related to the recurrence theory. But, so I was wondering if any of this works. Okay, thank you.
Any other questions? Any online?
Yeah, I will ask. Like, if you take the discrete spherical maximal function, and
Spherical.
yeah, so like, is it behaving like, does it behave like Euclidean on itself here, or?
So we have a result with Mirek and Szarek, which says that the dyadic discrete spherical maximal function has dimension 3 bounds.
Okay,
but
but the
the
acronym one you are saying.
Yes, but the discrete spherical maximal. So what you are saying is this. So now you compute not the lattice points in a ball,
Yes.
but the lattice points in a sphere. So this is the radiation of a sphere, and you compute the lattice points there, and this is now more number theoretic, because to even realize that it has some points is not trivial. Okay, but then if you are able to control this this average, then you immediately are able to control the ball average, because the spheres dominate the ball. So this is harder, but still for when p is equal to 2 and we consider the dyadic subminimum, we have a result which says that this has dimension 3 bounds, but not, I mean, even for the ball we don't know that the full maximal function is bound. But on the other hand, those sets resemble each other. When for example, what do I mean by that? When t, this parameter here, is very, very small, then essentially most or almost all of the sets inside the ball will lie on the surface of the sphere. So they are quite close in a way, but not the same. So it would be interesting to study the general subminimum here as well, but we don't even know what happens for the ball. So this is why. So here, for example, in the proof here, some tools from number theory go into picture, like solution to worrying problem and Hardy-Littlewood circle method. So I didn't want to mention it here to not to confuse even more the number of different topics that were before. But yes, there are some partial results here.
Yes. Like one more question. Like, if I take the full maximal, the spherical one, even the boundedness is known, right? Like
the boundedness is known, and the range when it's bounded is different than the continuous. But I don't remember exactly how. So
okay.
in the continuous, I think that full is bounded maybe for d
Yes.
something like this, d minus 1.
Yes. Yes.
And in a discrete, I might be mistaken, but it's something different, like maybe this.
I see. Okay.
So asymptotically, when d goes to infinity, they all almost cover the full interval, but they're not the same. So who knows? So already for the sphere, by the way, there is no comparison principle. So it's not completely obvious immediately if the spherical maximal function for very large scales is fine, because there is no. You cannot really say that the number of lattice points in the sphere is the same as the surface of the sphere. You can say it for the ball. Like when the radius of the ball is very large, the number of lattice points is almost the same like the size of the ball. But here actually, the number of lattice points here is related to a solution of Warring's problem, and there is some leading number theoretic factor here that depends on t. I don't remember what is the symbol, but it's called, I think, the principal. Sorry, forgot about the name. But there is a leading coefficient here that oscillates, and then there is something like t to the power t half minus 1 or something like this. So it's not clear even to justify this, whereas for the ball, if t is very, very large, it's obvious that the number of lattice points will be the same as the size of the ball. So this makes it more number theoretic.